Okay, well, it's good to be here. I think of AIR as one of my most important affiliations, and it's nice to have the opportunity to talk to folks at AIR about something near and dear to all scientists' heart, namely replication. So I'd like to start by just pointing out that replication is a concept that is absolutely central to not only the rhetoric of science, but the logic of scientific inquiry. Replication is, at the center of Popper's explanation of how scientific knowledge can be gained, why it is we gain knowledge from doing experiments. Replication is also part of the rhetoric of how science can be self-correcting. The idea is that errors are supposed to be discovered when we can't replicate things, and that's how science can be sort of a self-correcting, knowledge-generating process. And in some areas, people would probably go so far as to say you can't really have a discovery, or you can't have evidence without replication. And what you might think, given the central place in the rhetoric and in the logic and in the philosophy of scientific inquiry, that there'd be a big literature on replication. And a recent paper by Schmidt, you sort of put it as I have it on this particular slide here. You'd sort of expect that there'd be a big literature on replication that would involve definitions of replication and methodology for replication and prescriptions for doing replication. You'd also expect to see a lot of replications in the literature, but he points out just the opposite is true. Now, there's been some literature on replication. It's mostly been of the order of it was in the philosophical literature. There's been a fair amount, a few papers anyway, about replication in psychology over the last few decades. But those papers have mostly really been addressed the issue of, how should we think about replication? When is a replication study on a kind of a conceptual basis? And most of those papers that have been extracted from either the philosophical or the psychological literature, I would contend, talk about one sort of crucial distinction in replication, something that Schmidt calls direct replication, which is trying to repeat an experimental procedure and see if you get the same answer, versus conceptual replication, which is where you try to test the same hypothesis using different methods. I'd like to talk today about what Schmidt would call direct replication, and it seems and even simplifying what we mean by replication to the domain of direct replication, it's interesting how much more complicated replication is than it seems on the face of it. I was going to put a subtitle on this talk that was going to be replication, and then the subtitle was going to be, it's not as simple as it seems. And that's really the theme of this particular talk. So what I'm going to concentrate on in the talk are these 5 things. I've already sort of begun to talk about a little bit about the fact that there's surprisingly little written about replication. Many of us think that the reason is that scientists think replication is so obvious you don't need to sort of think about it. We all know how to do it. It's just you did a study, you want to find out if the results replicate, you do it again. Maybe if you're going to get fancy, you do it again better than the first time. But essentially, that doesn't seem like there's really much to talk about. And I'm going to try to argue today that there's a lot more to talk about. I'm going to talk a little bit about the replication crisis, then I'm going to focus on 3 things, which are things people think they know about replication that are more complicated than they actually may recognize. One is the idea of definition of replication, that it's when 2 studies that have been conducted replicate one another. The second is how you'd actually go about doing a statistical analysis to sort of decide whether that's true. And then third, my 6th item on the list here, a little bit about the design of replication studies, which seems obvious, but I'm going to suggest is way less obvious than it seems. So the replication crisis got started, I think, or concern about it got started particularly in medicine by papers like this one that was written by a friend of mine, John Ioannidis, who at that time was an obscure medical epidemiologist working in a university in central Greece. In the course of a few years, he found himself a professor at Stanford Medical School running a big research center, and part of the reason was papers like this one. Of course, this paper, Why Most Research Findings Are False, has a nice snappy title. He wrote another paper roughly the same year, which has a less snappy title, Contradicted and Initially Stronger Effects in Highly Cited Clinical Research, but actually may have had a bigger impact because of what he did. And just for those of you who don't know, what John did was to go find he found about 50 studies that were highly cited in the medical research literature, that is over 1,000 times. 1,000 citations is a lot for a recent paper. And then he asked the question, did those results get replicated? Did anybody replicate these studies or try to replicate the studies? And the surprising finding was that among the studies that there had been an attempt to replicate, all the effects were smaller. Some of them were actually different, that is, they contradicted the original study. And this was a big surprise in the medical world. It was not what they expected. Many of these studies were randomized trials. I mean, we're not talking about slouch studies. They were studies published in reputable medical journals that were deemed important enough that 1,000 people cited them in other medical research studies. And so the discovery that these things weren't replicating as well as people expected was a shock. It turns out, though, that over the ensuing decades, this was just the tip of the iceberg. It turns out that in other kinds of medical research, for example, preclinical kinds of research on things like drug discovery, similar kinds of exercises discovered that the replication wasn't as good as people expected. This is, I'm just giving an example of a paper that was in Nature about 6 years ago. There was another paper in Nature a little more recently that found similar results. Things just didn't seem to be replicating in the way that scientists expected high-profile medical research or preclinical research to replicate. This got the NIH kind of excited, meaning worried, and they announced with great fanfare attempts to try to enhance the reproducibility and replicability of medical research. And I will not go into the kinds of things that the medical community has pushed, but they include things like registration of studies, in fact requiring registration of studies before they're allowed to be published in major medical journals. And this has been a big initiative to try and help address the replication crisis in medicine. The jury's out as to whether or not they've been entirely successful. The point is there's been a very serious response, and I think people like Collins and Tabak from the National Institutes of Health understand that this is an existential crisis. There's no reason to spend billions of dollars on the National Institutes of Health if the results that they produce are no more reliable, no more replicable, have the same status as evidence as things that are way cheaper to produce. And so that's, I think, why the NIH, for example, is taking it quite seriously. Well, so is NSF, and IES is beginning to worry about this issue. Of course, the replication crisis has come to psychology, and the APA is a little bit worried about it, as a matter of fact. Papers like this one that appeared in Science, where the Open Science Collaborative recruited 100 laboratories to reproduce 100 famous psychological research studies, got a lot of attention, largely because they didn't reproduce nearly as well as people thought they would. But let me mention that the design of this replication program, this particular one, is to find 100 studies and then find one laboratory to try and replicate each of them. So the design for each study is is the sort of conventional idea of what we think is how you ought to figure out if something replicates. You got to study an original study, somebody else does a study that's just like it, and then you compare the results. We'll get back to, by the end of the talk, you'll see why I called your attention to this design. Economics maybe should be concerned as well, because there's now a replication project in experimental economics, and their results are roughly like the ones in psychology. And the design that they used to assess replication was more or less the same as the ones that the psychologists used. And here it's important to recognize that they were sort of following the lead of the Open Science Collaborative, trying to sort of reproduce what they did in experimental economics. Okay. The thing, of course, that everybody in the scientific community is scared to death about is that the discussion has kind of entered the popular media, and that it may begin to erode the credibility of scientific evidence at a point where evidence of all kinds, and scientific evidence included, isn't exactly in the highest esteem of many people in the country right now. And so this existential crisis idea, I think, is really it really begins to be the existential crisis when the popular media pick up on it and say, well, so you can't really trust scientific evidence. Okay. Now I want to start addressing the three aspects of replication that I mentioned are not as simple as they might seem to not only the average citizen, but the average scientist. So I want to give a little bit of statistical background and say that this talk is going to be entirely concerned with the a situation in which you have exactly two studies, an original study and a replication study. But everything that I'm talking about is easily generalized to having more than two studies. And some replication projects have started using more than two studies. So probably is no surprise to those of you who know anything about the work I've done in the past that I think the right way to think about this problem is from the meta-analytic perspective. That we can think of a study's finding as being summarized by some kind of effect size index. And I'm not committed to which index it has to be. It could be a standardized mean difference, could be a regression coefficient, whatever. You know, this may be too simple to characterize every kind of research that's done, but much of the research that's done throughout the social sciences focuses on a single effect, or at least that's at least part of a big part of the message of the study. And I think it's probably smart to figure out if we understand what we're doing with respect to studies that can be summarized by a single effect size before we consider more difficult problems. So bear with me, and let's stipulate that in at least a lot of cases, it's sensible to summarize the result of a study by an effect size index of some kind, being kind of agnostic about what it might be. And then the implication of that is that the study's true result is the effect size parameter that's associated with that study. The effect size parameter, which I'm using the symbol theta to represent, is the effect we'd observe if the sample size was essentially infinite, if there was no estimation error. Now, we don't ever observe theta because we almost never have infinite sample sizes in our studies, or even, you know, usually we have sample sizes that are too small for at least for our aspirations. So we never observe theta, but we do observe an estimate t of theta, and I'm going to make the not an altogether wrong assumption that the variance is essentially known, and that's the typical kind of simplifying assumption made in a lot of meta-analytic situations. And for most large-scale studies, there is some variance, but it is known pretty well enough to, at a first approximation, say it's essentially known. It's sort of like what I'm saying here as well. You did a t-test on your 100 observations, but you could have done a z-test and gotten the same answer. So making that set of statistical assumptions, then we have to recognize that because theta is, the estimate of theta anyway is the true result of a study, any definition of replication has to be in terms of thetas, not estimates. In other words, if we're talking about whether study A replicates study B, and if the theta for study A is the true result of study A, then we need, whatever definition of replication we're going to come up with has got to involve comparing the theta in the first study and the theta in the second study. So just for some notational convenience, if theta 1 and theta 2 are the effect size parameters in two studies, and if T1 and T2 are the effect size estimates in the two studies, and they have estimation error variances V1 and V2, that's the only real statistical notation I'm going to need to define here. I'm going to define one other quantity later, but it involves these things. Then, we could begin to talk about, well, what does it mean to say study A replicates study B? And one definition of replication is what I would call exact replication, and that is that study A replicates study B if the theta in study A is the same as the theta in study B. And if we number these studies 1 and 2, that means that you have exact replication if the two effect size parameters are the same. In other words, if theta 1 is equal to theta 2. This is a simple definition of replication, and it's a definition of replication that's kind of used cavalierly. It's not actually called replication in that case, but this sort of definition of do the studies agree has been used in meta-analysis, to define effect homogeneity. But I'm going to argue that this is actually not a very useful definition of replication for scientific purposes. And the reason I'm going to say that is it's just too ambitious to fit reality. In real studies, in good sciences, exact replication is not something that's possible. And I'll give sort of 3 lines of evidence and then show some examples. First example was a paper that Steve Stigler wrote in the Annals of Statistics 40 years ago. And what he did was to look at historical data on physical constants, and his conclusion was that in order to get a good analysis without robust estimators, to get a good sort of analysis of the physical constant data, you had to trim it. You had to trim 10% on the top and the bottom of the distribution of estimates. So in other words, what Steve was saying is, you can do a good job of analyzing physical constant data as long as you throw out the 20% most extreme data. That's important because it says basically that there was not good replication across those findings. Then second example, second line of evidence comes from something called the particle data group. The particle data group is headquartered at Berkeley and CERN. For the last 50 years, they have been doing meta-analyses of all of the high-energy physics experiments done in the world, and every 2 years they put out a massive document called the Review of Particle Properties, which summarizes those meta-analyses. The reason they do that is they're trying to get the best values of particle properties that they can, because those are values support other experimental work in high-energy physics. So these are the particle data group stuff includes mundane things like the mass of the electron, but also more exotic things like branching fractions and lifetimes of various particles and things like that. Why do I mention the particle data group? Well, they do quantitative analyses of replications, and they find that they have to throw out about 40% of the estimates in producing their best values. They throw them out for various reasons, but one of the reasons is the estimates are too different from most of the other estimates. And even after that, it turns out they still allow some tolerance for disagreement among the studies. The third example, which I'm going to give you some some more precise examples of, are the fundamental constants of mathematical physics. If you there's no reason for you to know this, but it turns out that there's a handful of so-called fundamental constants of mathematical physics that are crucial in various different fields and have been estimated for a century, and with attempts to get high accuracy estimates so that they can support various other kinds of calculations in science. And so I'll start with the speed of light, and I'll just say what's here. I can have to decide where's the best place to point my laser. Well, what's here in these graphs is, and you really can't see it I can't see it when it's on the screen. So I'm going to step over to the screen and just say that on the x-axis here, there are years in which the experiment was the year in which the experiment was done, and then there are lines and dots, and the little dot is the estimate from that experiment conducted in the year that's indicated on the x-axis, and then the sort of whiskers that extend on either side of the dot are the confidence intervals for those estimates. And the important thing to notice about this graph is that if all of these measurements of the speed of light were actually estimating the same thing, you'd expect all the dots to line up, and you'd expect all of those confidence intervals to overlap. And the major point is they don't, and you can do a quick back-of-the-envelope calculation and convince yourself that these numbers are highly statistically significantly disagreeing with each other. And you might even think you're seeing a time trend between the earliest measurements and sometime just before about 1940. And in fact, there were physicists as late as 1940 who actually were arguing that maybe the speed of light is changing over time, and there's a secular trend in the speed of light, and that's what we're learning here. But some other physicists were very happy to be able to put that rumor to bed in the 1940s, as the estimates seem to have, some come back into line with, but not quite, with earlier estimates of the speed of light. Now, you might think that this little spot here, where the estimates are all getting close together, you might think that the 20th century is actually a century of great convergence among these estimates. But if you blow up the 20th century era, you see that there's still a lot of disagreement among estimates of the speed of light, even in the 20th century. And the speed of light, you might think, well, maybe the speed of light is something that's really hard to measure, and every other physical constant can be measured with great accuracy, and the experiments all agree. Well, not true for the other fundamental constants of mathematical physics. There are things like the fine structure constant and Planck's constant, the electron charge, the electron mass, and Avogadro's number, all of which have been measured over time, and all of which show statistically significant disagreement over time in the measures that have been made of them. For more fun, you can look at measures of the fine structure constant, or the inverse of the fine structure constant, which is a fundamental constant that's important in quantum electrodynamics. And you can see that there's a lot of disagreement among that chart happens to be turned on its side, but there are experiments conducted at different times, and they get pretty different answers. And an example from the particle data group that they use to kind of justify doing meta-analyses rather than looking at single high-accuracy experiments. Single high-accuracy experiments of the proton mass showed that the proton mass changed by over 5 standard errors between 1960 and 1975. Something we're pretty sure reflects problems with the experiments rather than changes in the underlying physical world. Okay, so an alternative to exact replication would be to define some difference between the true effects of studies that is small enough to be negligible. And you could define that in terms of just the difference between the effect parameters, but for various reasons, which I won't go into in great detail here, but you'll begin to see some of the reasons later, it's actually, it has proven to be more useful to define approximate replication in terms of a parameter that I'm calling lambda here, which is really the squared difference, not the difference in the effects found in the studies, but the squared difference in the effects divided by the sum of the estimation errors. And the reason this quantity is useful is that it provides one way to define what a negligible difference is. And so if of course you define lambda to be 0, you'd be saying, well, exact replication is my definition of replication. But another way of defining replication is to say, well, you can have approximate replication when the value of lambda, this sort of standardized difference, if you will, is standardized squared difference, is less than some small amount lambda naught. Now, of course, all I'm doing is showing you algebra. You might say, well, yeah, there's nothing wrong about the algebra, but how could scientists possibly, come up with conventions like that? Well, it turns out scientists have come up with conventions like that. The particle data group uses a convention that's the equivalent of saying lambda less than a quarter is negligible. They're not saying 0. They're saying if we have a lambda that's smaller than about 0.25, we would call that the moral equivalent of agreement among experiments. In personnel psychology, something called the 75% rule has emerged. And the idea there is if 75% of the total variation in estimates is due to estimation error, then the remaining 25% is probably due to other biases in things that don't constitute real disagreement. And that corresponds to a lambda of about a third. And then in medicine, the Cochrane collaboration in their handbook, their statistical handbook, declares that a certain value of I squared, which is again is a parameter convertible into lambda, of less than about 2/3 is what they would call not important. And the point here is that in 3 very different sciences, they've chosen a convention for defining approximate replication that can be expressed in this metric of lambdas, and saying that lambda less than some target amount, lambda naught, constitutes a negligible disagreement, or in essence, replication. So here's my major point 1. Defining replication is not as simple as it seems. Exact replication is logically appealing, but it's not very scientifically useful. And that leads us to the idea that approximate replication is probably more scientifically useful, but it's not as simple because it involves defining this negligible difference lambda naught, and that has to be defined as a social convention among scientists. There's no analytic derivation that's going to tell you what the right lambda naught is. It has to be something scientists agree on the basis of their own experience and whatever reasons led the physicists and others to agree on particular lambda naughts. I'll just mention that, I told you that the particle data group throws out a lot of estimates before they combine things, and even though they do that, they still have a little margin for disagreement among studies before they become concerned that they're not really replicating one another. Okay, so that's the first point. It's tricky to define replication in a useful way. So now I want to talk about statistical analysis of replication. There is a test for exact replication that is a sensible test involving this quantity Q, which is the squared difference in the estimates divided by the sum of the estimation error variances. And when you have exact replication being true, Q has a chi-square distribution with 1 degree of freedom. This is, in fact, the heterogeneity test that's used in meta-analysis for 2 studies. The way the test works is you calculate the Q and you reject the null hypothesis of exact replication if it's bigger than a critical value obtained from a central chi-square distribution, and for the 0.05 significance level, that critical value is about 3.84, which you might quickly realize is the square of 1.96, which you might remember is the critical value for the standard normal distribution, and it's not an accident. Now, a point to remember is that rejection of exact replication is a conclusive finding, but failure to reject isn't in the classical hypothesis testing framework. And so another way of putting that is that the test for exact replication puts the burden of proof on non-replication. Or to put it another way, this testing scenario is only conclusive if this test has high power, so that you can interpret a failure to reject as meaning at least that the effect was, we would have rejected with high probability if the effect had been at least so big. So what I'm saying here is that even if you decided exact replication was the way to go, there's a real serious issue of making sure for the procedure to be conclusive that the test has high enough power in order to be conclusive if it doesn't reject. Now, you could actually frame analyses of approximate replication with the same methodology that we just described for doing tests of exact replication. The only difference is that now we'd be testing a null hypothesis that lambda was smaller than or equal to some amount lambda naught, and the only difference would turn out to be that we would get the critical value not from the central chi-square distribution, but from the so-called non-central chi-square distribution, the distribution of Q, when lambda is actually equal to lambda naught, not 0. And just for reference, if we chose the 5% significance level again, and then chose lambda naught to be a quarter as the particle data group does, then the critical value for rejecting approximate replication would be 4.76 rather than 3.84. And if we chose a larger kind of margin of negligibility, allowed a larger amount of difference to count as replication, then the critical value would get successively bigger as we increase the value of lambda naught. And I've indicated what a few of those values would be on this slide. The reason that's going to turn out to be relevant is that it's the same test statistic, the bigger the critical value, the smaller the power is going to turn out to be. So tests for approximate replication will be less powerful than tests for exact replication. So that's just something to remember, but we know how to do the testing. But there's a problem kind of with both of the ways I've framed the test for exact and approximate replication. In both cases, the burden of proof is kind of on non-replication. But that's not how we usually set up our hypothesis tests. We usually set up our null hypothesis so that when we reject it, the conclusion is what we want to conclude. So suppose we want to conclude that two studies replicate, couldn't we just set up the testing scenario so that rejecting would mean that we accepted replication? Well, it turns out you can do that. That's sort of a way of putting the burden of proof not on non-replication but on replication. And how we would do it is by starting by defining some size of lambda that constituted approximate replication, and then setting up the null hypothesis to be that lambda was bigger than lambda naught, so that if we rejected that hypothesis, we would conclude that lambda was smaller than lambda naught. In other words, that the studies replicated. And that would be more in line with the kind of logic of hypothesis testing as we usually use it. We would test the null hypothesis of approximate non-replication in order to reject that hypothesis and conclude that we had approximate replication. And we could do that with the Q-test. It would just involve rejecting the null hypothesis of non-replication if the Q was sufficiently small. And it's not statistically an advance to do that. It's just a reframing of the hypothesis testing. But the point of all of this is that just like the definition of replication is not as straightforward as it seems at first, there are complications there. The analysis that you might want to do to determine whether replication has occurred is not as straightforward as it might have seemed. I said earlier that approximate replication is a more scientifically attractive, more scientifically useful concept than exact replication. But one of the consequences of moving to approximate replication is the test is less powerful. Well, if the alternative would be to place the burden of proof on approximate replication, that sounds pretty attractive, but it turns out when you evaluate the power function of those tests, the power is even lower than that of the tests for approximate replication. Although this is not quite a fair comparison, I'm just telling you, having looked at a bunch of these computations, it's putting the burden of proof on approximate replication, logically appealing though it is, it makes it really hard to design studies that are going to be sufficiently conclusive that they're worth doing. So that's kind of a suggestion that we ought to think a little bit about the design of replication studies. And of course, I started by saying everybody kind of thinks that's obvious. You know, if you want to figure out if a study replicated, you just do it again and then compare the results. Well, I'm going to sort of spend a few minutes now trying to convince you that that's not as straightforward as it sounds. So I want to remind you that in every test, rejection of the null hypothesis is conclusive, and we hope to ultimately conclude that studies replicate, at least if we're on the side of solving the replication crisis. And that means to ensure a conclusive result, we need to make sure that our ensemble of studies, the original study and the replication study, yield statistical analyses that have adequate sensitivity. You know, this is a problem of design. People haven't thought about it this way, that, you know, the problem in understanding replicability is to design an ensemble of studies that together give you results that are conclusive. The problem becomes that the design includes both the original study and the replication study. And both the original and the replication study have a statistical uncertainty, and they both have both those uncertainties have to be taken into account in evaluating the design of a replication study. So now I have one more little bit of statistics to tell you, and that is that the power of the Q-test is determined by this quantity lambda. I said there were good reasons to characterize the degree of replication, or what constitutes approximate replication in terms of this quantity lambda, the squared standardized difference between effects. Well, it turns out that this lambda is a natural way of describing how false the null hypothesis is, and the power function of the Q-test depends on lambda. So to compute the power of a Q-test, which, remember, the reason we're doing this is to ensure that the replication study, the ensemble of replications, the ensemble of studies we're using to study replication is conclusive. And in order to determine whether it's conclusive, we have to know that the Q-test is powerful enough to detect a real difference that we consider big enough to be important. Then that raises the question of, well, what is the smallest, what is the biggest difference that's negligible, or what's the smallest difference that's non-negligible? And I argue that you can think about that, and there's one kind of obvious answer. It's not, it may not be the most refined answer, but if you ask, well, how big could the difference between the effect size parameters in the first study and the second study be, and still have that difference be considered qualitatively negligible? It's sort of the equivalent of sort of saying, well, there's an effect theta 1 in the first study, and how big a range around that effect could I declare to be a zone of negligible differences? Well, I think the answer to how big that zone could be is if the result of the second study has a different sign than the result of the first study, you're not going to call those differences negligible because they're qualitatively different results. So that means that the biggest negligible difference between two studies in their effects has to be smaller than theta 1. In other words, if theta 2 is just a little bit bigger than 0, you might still have a fig leaf of a chance of calling it the same as the second effect because they have at least the same signs. But if they don't have the same sign, I think it's really tough to tell the story that that they really got the same results. Okay, well that has an implication immediately. And the implication is given at the bottom of the slide there, that says that the biggest negligible negligible difference is, or the smallest non-negligible difference, is on the order of theta 1 squared divided by v1 plus v2. All I've done is just substituted theta 0 for theta 2 there in computing the non-centrality parameter. Everybody follow how I got there? Okay, so now we've sort of pointed out how big the non-centrality parameter is going to be in the most powerful test for, let me see if I've written this down, for replication. So the argument here is a little bit tricky, but the power of the test is an increasing function of lambda. So the bigger the lambda, the bigger the power of the test. We just discovered that the largest negligible non-centrality parameter for the test is lambda is something a little less than theta 1 squared divided by the sum of the estimation error variances. Any other negligible difference must be smaller. And so what that means is that the maximum power of the replication test has to be less than when lambda is theta 1 squared over the sum of the estimation error variances. So we figured out what the power must be of the best test we can do for replication, the most powerful test we could do for replication. Now, that by itself doesn't say anything, but then you have to think about how does this line up with the power of the test for a treatment effect in the first study, in the original study? Well, you can show that the power of the test that there is an effect, a non-zero effect in the first study, is determined by a non-centrality parameter that's theta 1 squared over v1. This is just saying that the test statistic for testing whether theta 1 is 0 would be t squared over v, and it would have a chi-square distribution with 1 degree of freedom. And so, in fact, you can put it on the same scale. The power is determined by something on the same scale as the replication test. So combining this statement and this statement, the implication is that the power of the test for replication has to be less than the power of the test for treatment effect in the first study. And actually, it turns out that it's not just that. The power of the test for replication has to be less than the power of either of the two studies being used to assess replication. So the power is less than the worst of the two studies in terms of their power to detect a treatment effect. Now, that should give you pause, because in many cases we carry out studies that are just barely powerful enough for us to convince ourselves that we've got a decent shot at detecting an effect if it's there. What we're finding out is the test for replication is, at best, worse than the test we've got for treatment effects in the worst study of the lot, but it's really worse than it seems, because the only way you can get the replication test to have the same power as the worst of the two studies that you conducted to assess replication is if the other one of those two studies has essentially an infinite sample size. And of course, remember our prescription about how do you design a replication study. Well, you just do the same study all over again. Well, that would say that you would do a study with the same sample size, the same estimation error variance. And if that was the case, then essentially the non-centrality parameter associated with the test for replication wouldn't be theta 1, the maximum power wouldn't be associated with a non-centrality parameter of theta 1 squared over v. It would be associated with theta 1 squared over 2v. And that means that the power would be considerably less. For example, if the original study had a power of 80%, which would correspond to a lambda of 7.85, then if you do two studies that have the same sample size, same error variance, then the power of the replication test would be 51%, even though both studies had a power of 80% to detect the effect they were looking for. And in fact, if you want to know how big a study would you have to do as study 1 in order to get a replication test that had a maximum power of 80%, then the answer is you'd have to have 98% power in both of the studies that were being used as the ensemble to study replication. And all of this is assuming that what you mean by agreement is just that the two studies, that you have a sensitive enough replication test to detect whether the two studies have the same sign. And if you decided, for example, that study 2 having an effect that was 90% smaller than study 1 didn't count as replication, then the test that would rule out that hypothesis would be considerably less powerful. So what's major point 3 here? It's that it may be impossible to obtain a test for replication that's sensitive enough to be conclusive from a single replication study. You can increase sensitivity with more studies, but even then you have to be a little bit careful. We really need more work on the design of ensembles of studies for testing replication, because remember, I asked you to think about, recall the design of the Open Science Collaborative's replication project. They had 100 studies, each replicated once, which we just saw is probably not a very good design for finding conclusive results about testing replication. Some people have suggested, in fact, the Open Science Collaborative has done this too. They've suggested that, well, really we ought to replicate each study more than once, and then we ought to compare all the replications with the original. Now, it turns out that that sounds like a good idea, and it sounds like it's going to help you, but it turns out it doesn't. Because what they're saying is essentially, do all of these replication studies and compare the replications with the first study. But that's the logical equivalent and the statistical equivalent of creating a synthetic study out of all the replication studies, and then comparing the synthetic study's result with the original, and it has exactly the same limitations that I just talked about with respect to comparing two studies. So that's an example of a design that sounds plausible, but in fact is just as problematic as the two-study design. It is possible to increase the sensitivity of tests for replication, but only by doing tests that compare all the studies with each other, that don't privilege a first study and compare other studies with that. And it turns out that you can develop designs that actually have adequate sensitivity under this new scenario of comparing all the studies with each other. But it's not the thing that has come most immediately to mind of people doing these kinds of replication studies. One more point is just the one I made, that the replication projects in psychology and economics haven't really considered the issues we've talked about today. And in all fairness, I don't think they were aware of them, because I wasn't aware of them until I started thinking about this pretty recently. And in fact, you are some of the first people to hear this work. Aside from a briefing at IES, you're the first audience to hear some of these things. And so I think that you can't blame the Open Science Collaborative for not knowing stuff that wasn't known. On the other hand, these kinds of findings do raise issues for people interested in replication and interested in trying to help us fend off what I think would be the ill consequences of a replication crisis in education if it were to hit and become widely known. So with that, I'll stop. Thank you.